Hi everyone, this is Mr. Montgomery. Welcome to Lesson 4.4, Sigma Notation and Writing Area as a Limit. In this lesson, we're going to express the limit of a Riemann sum in integral notation, and we're also going to do the opposite, writing integral notation as the limit of a Riemann sum. And these are our learning objectives from the College Board. LO 3.2a, subparts A and B. Interpret the definite integral as the limit of a Riemann sum and express the limit of a Riemann sum in integral notation. So we're talking a lot about notation in this section, and there is a lot of notation here to talk about, but we also want to focus in on a good conceptual understanding of what Riemann sums are and how we can use them to approximate the area under a curve. So in talking about Riemann sums, I want to share with you guys a resource I found from the textbook Calculus Early Transcendentals 3rd edition by Briggs, Cochran, Gillette, and Schultz. And what it is a CDF file, computational data file that was created using Wolfram Mathematica and related to Wolfram Alpha. You need a CDF player, which you can download for free if you want to interact with these files directly, but I'll just show you in the video what this looks like. So this is from section 5.1 of their textbook. It's figure 5.05. And what they've done is they've taken the function v equals t squared, and they have drawn a rectangle over the interval from 0 to 8. And you can see that the height of this rectangle is given by this particular y value on the function. And so the idea is that we could use the area of this rectangle to approximate the area under the curve. And I will tell you, this is not a great approximation. I mean, look at all this empty space here above this part of the rectangle. But the idea is that we're using the midpoint of this rectangle on the function. And so that means that, yes, I do have all this empty space over here, but over here on the left side, I've got this part here that is being counted, even though it's not under the curve. And so if I were to take this maybe and flip it over here, it would compensate for some of this, but as you can imagine, it would still fall short. So it's a good first shot at approximating the area, but it's not great. Why would we even do this? Well, the idea is that calculating the area of a rectangle is easy. You just do base times height, whereas finding the area under this curve is a complicated process if we don't have a strategy. So what if we took, and instead of using one rectangle, what if we took the width of this rectangle and we cut it in half? Then we could put two rectangles underneath and then let the midpoints of those rectangles go up and touch the curve, and we would have two rectangles that we could add together to approximate the area under the curve. Here's what that looks like. So in this case, I now have a smaller rectangle, shorter. Its width is only 4 instead of 8, and it only goes up this far until it touches the function at its midpoint. And the midpoint of this rectangle comes all the way up here. Now the idea is that by increasing the number of rectangles, we will get a better approximation of the area under the curve. And I could take this triangle and flip it over here, and it would take up a much greater space. This one, flip it over here, we're not quite there yet. We still have plenty of white space that we've not measured. But we've gone from 128 to 160. Now the idea is that all of these rectangles will have the same width. So even though I had one rectangle whose width was 8. As soon as I went to two rectangles, both of those rectangles had a width of 4. Yes, the y values, the heights of the rectangles change according to the function. But let's shrink the width of the rectangles again. Let's shrink them this time and make the width 2. And that way we can have not 2 but 4 rectangles on this interval. And so here we have a little teeny tiny rectangle and then a slightly bigger one, and you can see how that triangle is beginning to closely approximate the white space. This one is closely approximating the white space. It's getting better, and our area is 168. All of these rectangles have different heights according to the value of the function, the y value of the function, and again that corresponds to the midpoint of these rectangles. And let's make the width smaller even still. And now we have 8. And with 8 we go from 168 to 170. And you can see we're getting a better approximation of the area, but there's still plenty of error in this. So once again, let us cut the width of those rectangles in half and double their number. N equals 16, 170.5. N equals 32, 170.625. Now you can see this limiting behavior, right? Do you see that the area under the curve is actually converging to a value as the limit of the number of rectangles? Well, what are they doing? They're increasing. We're increasing the total number of rectangles. What is the number of rectangles approaching? Well, as the width of the rectangle approaches 0, the number of rectangles, or the number of subintervals, approaches infinity. So as we let the number of subintervals approach infinity, our area begins to converge on a value that would be the exact value of the area under the curve. So that's what they mean when they say, by creating an infinite number of partitions, the summation will produce the exact area under the curve of the function. What do they mean, summation? Well, we take the areas of each of those infinite number of rectangles and we add them together, we sum them up, and we get the total area under the curve. And so here is an expression of a Riemann sum. And so it is the width of the subinterval. How do you do that? Well, if you're on an interval from A to B, to find the total width of that interval, you just do B minus A. And if you divide it into n subintervals, then the width of each interval would be B minus A divided by n. Now remember how we said the height of the rectangle was given by the particular y value from the function? So for n subintervals, we're going to have k, we're going to index our subintervals using the index k, as k goes from 1 to n. So to find the area of any one of those rectangles, we would multiply the width, b minus a over n, times the height, which is the corresponding y value. And so the sum of all those areas would be b minus a over n times y1 plus b minus a over n times y2, so on and so forth, all the way out to yn. Now for convenience, they factored out b minus a over n, and we're multiplying by the sum of all of the y values. Looking at this, it may not make sense geometrically what's going on until you distribute this, knowing that this is the width and these are the heights. And so we're adding up a sum of all of those rectangles. Now what about the exact area? Well, to do that, we're going to have to find these y values by using the function. And so y1 is actually going to be f of x1, where x1 is the x value corresponding to my first rectangle or my first subinterval. And so xk, x sub k, this is the expression that we use to represent the x value that corresponds to the given y value. Now in the CDF that we just looked at, we used the midpoint of the rectangle. So that means that this x value would correspond to the x value of the midpoint of that rectangle. What they're going to do in the next few examples is look at a right endpoint approximation. And so what that means is that instead of having the midpoint of the rectangle touch the function, it's going to be the right endpoint. Now this is going to give us an overestimate for the area because all of the remaining part is going to be outside of the curve if we were looking at a function like v equals t squared. So how do we calculate the individual xk's? Well, we take the lower value of our limit, a, and we add to that delta x, that's the width of our rectangle, and we multiply that times k, which is the index of the rectangle that we're looking at. And that just gives us an x value located on the x-axis for the midpoint of the particular triangle that we're looking at. I'm sorry, rectangle that we're looking at. So the sum written in sigma notation is going to be the definite integral from a to b f of x dx. And this is going to be equal to the limit as n approaches infinity of the sum from k equals 1 to n. K is my index, n is the total number of partitions. F of xk, that's the y value, times delta x, that's the width. So the y value is the height of the rectangle, delta x is the width of the rectangle.